Science Friday is brought to you by Progressive Insurance. Here's a helpful fact you might not know yet. Drivers who switch and save with Progressive save over $900 on average. Pop over to Progressive.com, answer some questions, and you'll get a quick quote with discounts that are easy to come by. In fact, 99% of their auto customers earn at least one discount. Visit Progressive.com and see if you can enjoy a little cash back. Progressive Casualty Insurance Company and Affiliates national average 12-month savings of $946 by new customers surveyed who saved with Progressive between June 2024 and May 2025. Potential savings will vary.
WNYC Studios is supported by Alienware.
Alienware's back-to-school event is the perfect time to score top gaming gear with incredible features and advanced engineering to go beyond performance. Start your Alienware journey with the Alienware 15 gaming laptop featuring Intel Core processors. Game, live stream, and multitask for hours on end. Pair your incredibly smooth gaming experience with immersive visuals and sound by saving on sleek Alienware monitors, headsets, and more. This limited time sale awaits you now at Alienware.com/deals.
Hey, it's Flora, and you're listening to Science Friday. Some dark summer night, head outside and look south for the constellation Sagittarius. A bit to the west, where Sagittarius meets the constellations Scorpius and Ophiuchus, is the center of our own Milky Way galaxy. It's about 26,000 light years from Earth. And the center is hard to see because interstellar dust blocks our view. And so for a long time, just what was there was a matter of debate. Dr. Andrea Ghez developed a way to peer through that dust, allowing precise observations of the orbits of stars close to the galactic center. And what she found in the center of our own galaxy was a supermassive compact object, which has all the hallmarks of a supermassive black hole. She shared the Nobel Prize in 2020 with Reinhard Genzel for the discovery. Today, we're going to talk to Andrea Ghez about this game-changing discovery, what we've learned about the galactic center since, and her own orbit in science. Andrea is a professor of physics and astronomy at UCLA, where she heads UCLA's Galactic Center group, and she's with me now. Welcome.
Hi, Flora. It's great to be here.
Do we know what a black hole is?
Funnily enough, we actually don't. I mean, we know that it's an object whose pull of gravity is so intense that nothing can escape it, not even light, but we don't have the physics to describe it.
That comes as a surprise to me because I feel like we use the shorthand a lot for not knowing exactly what it is.
I think the fact that we don't know what it is part of what makes them so compelling.
I want to get into that. I mean, why did you originally pick this problem of what was in the center of our galaxy?
You know, it's always interesting to think back about why you got into a certain area of research. If we just start at that moment when it started, it was that this was a problem or a question that was percolating around in the scientific community. And I had a technique and an opportunity to address it. So it was right place, right time.
Was there drama around it? Like when you say it was percolating, were people arguing at meetings? What was the level of percolation?
Well, there was a lot of discussion around this. I wouldn't say, I guess it was. It was a lot of argument about whether or not there could be a supermassive black hole, not only in our own galaxy, but galaxies that sort of look like ours. They're very calm at the center. So they're very different than why we started to think that these really massive black holes, what we call the supermassive black holes, could exist. So in a sense, the opportunity to answer that question could best be addressed at the center of our own galaxy.
The citation for the Nobel is for a supermassive compact object that looks a lot like a black hole. I'm paraphrasing. Are there other things it could be?
Today, we've ruled out all the alternatives, but I think it's a great citation because it leaves room for theoretical ideas to come in and say, actually, this isn't a black hole. The whole exercise or proof is to show that there's a lot of mass inside a very small region. But that region technically has to be smaller than what we've demonstrated. So there's some wiggle room, but there's been today no alternative explanation, and we're pretty close.
Well, give me some details on that. So when you say it has to be smaller, like how much mass and at what size?
So the mass that we know, there's no debate about this. We know that there's 4 million times the mass of the sun inside a region that corresponds to roughly the size of our solar system. So in our solar system, we effectively have 1 times the mass of the sun. And here, this is a region where we've crammed in the effective mass of 4 million suns. Now, we should all be skeptical. That's our job, certainly as scientists. So the ultimate proof would be to show that that's inside a region that's about 1,000 times smaller than what we've achieved today. This, however, has been a huge jump compared to where we were before.
Yeah, let's talk about that progression for you. I mean, what did it take for you to go from, oh, maybe it could be a black hole to, it's probably a black hole to, oh, yeah, I'm almost certain?
Yeah, this has been a multi-step experiment. And in fact, in the beginning, we only envisioned the first step. And even that first step, people were quite skeptical about whether or not we could do it. So the way we approached this problem was that we were interested in tracking the motion of stars at the center of the galaxy. And the reason stars are such a good probe of what's there is that what you're doing is tracking the gravitational influence of whatever is inside the orbit of these stars. So you know the mass is inside the orbit, so you really are inward bound. And these stars aren't sensitive or aren't affected by other forces. But we had to do several things in order to do this. One is you need a technique that allows you to discover the existence of those stars, the probes at all. And then you need to be able to see them move. And step one was just seeing the motion, not seeing the whole orbit, but just seeing, one could say, velocity or speeds of these stars. When I first started this project, was just at the moment when the Keck telescope, which at the time was the largest telescope in the world, was just opening. The bigger your telescope, in principle, the better your ability to see things that are separated by very small separations. So in other words, you really can get to the heart of the galaxy with big telescopes. So this was a really exciting moment of a telescope that enabled you, in principle, to do the work. But there was a challenge. The challenge was the Earth's atmosphere. The Earth's atmosphere is a problem for astronomers because it blurs out your ability to get to that theoretical limit. So you have to correct for that blurring effect. So I had worked a lot on a technique for doing this. In principle, to me, it was quite obvious that it should work at this telescope. And then you need to see the stars move. And the story I love to tell about this moment is that I was a baby professor, brand new, thought I had a good idea, put in my first proposal, and it got turned down. It got turned down because people didn't believe the technique would work. And even if it did, that we wouldn't be able to see the stars move. And I think it's important just to reflect back on not only where the scientific understanding was, but where the technology was. So to me, that really reflected that was an emerging technology, and it was a new telescope. And so step one, which is just to discover the stars and see their motion, that's where the debate was on multiple fronts. So it took us 3 years. We basically measured the motion on the plane of the sky with this technique. So basically you take a picture, you find the stars, take another picture, and you see them move. And you take a third picture in order to convince yourself that they're actually moving. That's just not a noise. Okay, so that's step one. That's a long explanation for step one. Step two is faster. If you think that there's a black hole, these stars should be going on orbits that are pretty short. And if you just take first year physics, you know that they should be going around a corner, basically a bend or an acceleration. And so we kept going. We added another 2 years, and that just dropped out beautifully. You started to see these stars make an arc. And once you have that, you can start to estimate how short the orbit should be. And it became clear that the shortest orbits would be 10 years. You've already gone 5 years. 10 years is less than a human lifetime. So you're kind of off and running on this next step. And that next step is to measure the full orbit. And at that point, step 3, you've made another step that allows you to increase the evidence from the beginning by a factor of 10 million. I mean, 10 million is an enormous number. And that's what this experiment has done.
I mean, listening to you talk, obviously you're taking the long view. Are you a patient person?
I am a patient person, but I only had a vision for 3 years at the outset. So in some sense, the fact that we didn't know, well, I mean, 3 years was going to get us pretty far, a factor of 1,000 better than anybody else had done. So that was good. The payoff has been so high that it's worth it. So I guess, yes, I'm a patient person.
Why is this supermassive object, compact object at the center of our galaxy? Like that seems like an interesting place for it to be. Does it have something to do with the formation of our galaxy? Is it true that black holes like to be at the center?
That is such a good question. Like, why is it at the heart of the galaxy? It is certainly true that the most massive object in a system will sink to the center of the system, even if it's not formed there. Today, we think that supermassive black holes are connected to the formation of galaxies, and that at the beginning they should be formed at the heart. But even if they weren't, they would ultimately sink down. This really gets to the question of how do these supermassive black holes form? And there's been a huge debate. When we first started to get into this experiment and produce the first results, people were asking at the time, how do black holes form? And do they form first and seed the galaxy? Or does the galaxy form first and result in the formation of the supermassive black hole? It's a bit like the chicken or the egg question, which came first. And today we've come to the idea that they form together, that they form synergistically, that whatever forms one forms the other. And in that scenario, you really do expect the supermassive black hole to be formed at the heart of the galaxy.
We have to take a quick break, but don't go away. When we come back, Andrea, I want to ask you about your trajectory in science and what questions you still have. So don't go away. You're an observational astrophysicist. I'm going to stir the pot. Has physics gotten too theoretical, do you think? Too far from observations and data collecting?
Absolutely not. I think there's a really interesting dance and a really important dance between theory and observations. It's really the heart and soul of how the scientific method works. Theory drives observations and observations drive theory. And in fact, for me, the most exciting moments as an observational astronomer is when we upset the apple cart and inspire theorists to think about, well, what else could this be? Or how do we rearrange the puzzle pieces to make all this hang together?
I mean, is that what the theoretical physicists love the best, too?
I suspect they would have a very different way of describing it. I love it when new theories, or actually theories, are in tension with one another. and there are observable consequences or something that you understand, if you could develop the next instrumentation instrument, you could actually solve it. That's what drives observations.
When the data was rolling in for you and you felt confident in it, did you get pushback? Did you have to fight for your idea?
Oh, absolutely. And that's really fun because that's what propels you forward. I mean, both the theory and the skepticism. In other words, it's telling you, yes, this is interesting. I mean, if you get critique, you know you've done something interesting. People are paying attention. And it's our job as scientists to be critical in the most positive sense of the word, to really assess how strong the evidence is, to assess what else it could be. And in part, that's what got us to go further. When we had only speeds, that the first stage of our experiment, people came up with all sorts of ideas about how those stars could be kicked and get to those high speeds other than just the gravitational influence of something massive at the center. And that forces you, or it inspires you to think about, well, how could I overcome this? So it really drives you, and also provides more fodder for justifying why you should be given more telescope time. I mean, if you would like to do it, that's one thing. But if others really demand it, that's a whole other level of necessity.
I mean, it seems like you have a thick skin.
I think one has to. Yes. Or develop the understanding that this criticism isn't personal. It's about the science. It's not personal in the sense of challenging your ability to do science, but just the questioning what the evidence really allows one to claim.
I mean, ideally, that's true.
Ideally, that's true. And of course, we're all human. So, there are low moments. But the great thing is, we're so lucky to be able to do all of this. And it is, I guess it is really important to have that interplay.
I want to talk a little bit about your path. Your dad was a professor, your uncle a physicist. I can imagine how they might have influenced you. But your mom ran a contemporary art gallery. And I wondered, did growing up around art influence how you approach science?
Oh, that's an interesting question. I've often thought about the way in which basic science has a relationship to art, in the way that art often forces you or encourages you to look at the world in a different way. That, from my perspective, art really helps us understand the world in which we live in, to expand our understanding. And in basic science, that's a very similar goal, that what we do with new instrumentation is to open up new ways of seeing things. And that expands our ability to understand the universe in which we live.
I feel like, relatedly, I'm thinking about the work of the Event Horizon Telescope folks and this picture of a black hole. And I remember when it came out, it was sort of donut shaped. And I'm curious what that image was like for you as a black hole person, like if it matched up or just your sort of response to it.
Yeah, well, I have a lot of responses to that. It's such an amazing feat of what that group did in terms of making an image. I think it's important to ask, well, what is the image of? Because remember, a black hole doesn't emit any light, so you can't actually take a picture of it. So what are you seeing? And in fact, at the outset of this experiment by the Event Horizon Telescope, they used to call it taking a picture of the shadow of a black hole. Now, admittedly, that's more words and maybe not as captivating, but that's actually what you're seeing. You're seeing light from behind the black hole. So it's photons now that are being gravitationally influenced to create this image. So in the very same way that we're measuring stars with a gravitational interaction, these guys are measuring the gravitational influence on the light. And, there are, in fact, nice ways in which these projects work together.
Was it cool to see, or were you like, that's just the shadow? Like,
No.
what was your emotional response?
No, I mean, you can have both thoughts at the same time. It's so cool. I mean, I've watched that project go from its infancy when it was a very difficult experiment and had a very long horizon. So I could certainly relate to the idea that if you advance technology, you're going to get new insight. And this was not an easy problem. So it was really cool to see the evolution of them going from a concept to actually fulfilling that vision and connecting these telescopes from all over the world at wavelengths that are much longer than what we use to construct this amazing image that has had incredible public impact. I mean, I think that's it's both a scientific achievement, but also an incredible public engagement achievement.
Can you ask new questions? Are you asking new questions with these new generations of telescopes?
Absolutely. I mean, one of the key drivers in all of this is, not only to prove the existence of a supermassive black hole, but to understand how do black holes work. And really what I'm saying there is, what is a black hole? How do we understand it from a physics perspective? And we think all the forces that we know about should connect. And one of the fundamental problems about black holes is that today we don't know how to make our description of gravity. And of course, our best description of gravity is Einstein's theory of general relativity, work together with things that are very small. So that's the description of quantum mechanics. And black holes definitely have lots of gravity and are very small. So you really need to connect these two fields. And we just don't know how. And that's such a fundamental question. I mean, when you start to ask, like, how does physics work? And that we have a breakdown in our description. So this is, this is pushing our understanding to the extreme. And so
this is a big problem to solve. Yeah.
This is not a minor problem. This is a big problem. And so any opportunity you have to understand, well, how does gravity work near these extreme objects is an incredible opportunity. And so these new telescopes and these next generations of experiments offer the potential to understand that question. And the assumption is that the closer you get to the boundary, which we call the event horizon or the Schwarzschild radius, which is the last point that light can escape from the black hole, the more insight you'll get. Now that I've said those words, it's important to realize that that's not the size of the object. It's an abstract size. Because today, with our current understanding, black holes have no finite size. They're infinitesimally small. But presumably, when we understand the correct physics, there will be some size, or at least this is our notion from the way we think about physics today.
I mean, I'm hearing you call out a lot of big gaps. How do you personally deal with this kind of uncertainty? Like, does messy data stress you out? What's your approach to that?
Actually, I think I'm most engaged when I'm most confused.
That's a tattoo, I feel like.
Well, I mean, it must
that should be on a t-shirt.
Yeah. Well, it's like a puzzle. You're right. There's an opportunity here. And I love puzzles. I mean, that's just a childhood passion and an adult passion, and both personally and professionally. So when things don't make sense, that's when there's an opportunity. to expand our understanding. And, it's the best situation is when you're confused, but not forever confused. It's just like it's almost like a jigsaw puzzle. Like you want one that you ultimately can solve. For me, it would be 1,000 pieces and not, 10,000
Right.
piece puzzle.
It's interesting, though, because I feel like a lot of people are can be overwhelmed by that situation. And I wonder if that's part of a key to your success is sort of not being facing it head on and being energized by a problem like that.
Yeah, I think one of the things actually that's a key to our education, and usually this happens in grad school, is to understand when a problem is solvable. You're looking for problems, but you're looking for the just right problem, the problem that is interesting, like is important to solve. So that's sort of one aspect that in principle could be solved. And then in last piece, that you have the skill set to solve, that you have the right combination of whatever you have, you come to it with a certain set of skills and understanding so that you can bring the knowledge that can push the ball forward. Sometimes you just have to leave a problem aside or understand, well, today you've reached the end of what you can do today, and you've got to either bring something, really think hard about, is this where you can make progress, or do you have to look someplace else? And, how far afield do you have to look someplace else? Is there more to be done there with something else? Or, do you have to start thinking about new problems? And usually scientists have a couple of things brewing in different states.
What are some of the lingering questions you have? Like, what's your burning question right now about the Galactic Center or otherwise?
Oh gosh, there's so many. Fundamentally, how does gravity work? So I think that just that's a really big one, and I think there are a lot of new things that are opening up that are going to allow us to probe that in new and exciting ways. I think understanding the interplay between black holes and their host galaxies is a really interesting problem. And there have been a lot of things that have been discovered, both by my group and others, that have upended our understanding of how that might happen. So I think that's another exciting area where you really see the interaction between theory and observations. I think that's another sign that there's more to be done, because when there's still residing tension. So yeah, those two areas, and of course the second one has just a ton of sub questions, and a lot that have been around for a while, and we've been making a lot of progress, and you can just see that there's exciting new avenues to be opened up, not only with just doing the project longer, because that's key to understanding the orbits, but new technology that lets you understand the nature of these stars. Like what are you seeing? And there's all sorts of weird, unexpected phenomena and kinds of objects. And those are really intriguing.
If you were just starting out now, would you stay in astrophysics? What would you do? If you could do it all again, starting today.
If I could start again, starting today.
Yeah.
So move the clock forward or me backwards. Oh yeah, no, move the clock forward. I think I would. I think it's such an exciting field. It sort of deeply hits us as humans. You can't ask any bigger question than this universe in which we live. And it's very humbling, right? Humbling to understand that we're pretty small. both in space and time. There's something, I mean, it's sort of a combination of things. It's humbling, it's awe-inspiring, and a little terrifying.
Which you like. That seems to be your jam.
Yeah, I do love it. So I think I would, if I had to go back. Well, I mean, if I had to go back and do it again and understand how exciting, and this just absolutely is. And I think there's been some appeal to this from a very early age. I mean, I was 4 years old when the first moon landing happened and people took their first steps. And that was exciting. I mean, that was exciting in my household, but it was inspiring as a kid to see that and to start to think about these questions.
Dr. Andrea Ghez is a professor of physics and astronomy at UCLA, where she heads UCLA's Galactic Center group. Thank you for joining me today. I really enjoyed it.
Thank you. It's been a pleasure.
This episode was produced by Charles Berquist. And if you're now thinking big thoughts about the universe, why not share them with us? 877-4SciFi is our number. Here for your comments and your questions. Thank you for listening. I'm Flora Lichtman.